Hi everyone, my name is Antons, and today I will show you Spectrum Compact Virtual Demo located at our website, which you can learn about many features and applications of our device.
SAF Tehnika produces a series of handheld microwave spectrum analyzers called Spectrum Compacts. There are in total 7 tools covering the spectrum from 300 MHz to 87 GHz, and the tool is perfect for field uses. I think it's widely acclaimed by numbers of RF technicians and engineers working in the field. It has a very compact size. It is easy to learn. Though in order to show off that despite its great size, it still has a lot of functionalities that allow you to perform most of the tasks you meet in your day-to-day activities. To show you what those functionalities are and make it more common, to help you make this decision about getting the right tool for you, our team created a virtual demo of the Spectrum Compact, specifically 2 to 8 GHz tool. Although the interface, the functions it has, well, they're very, very similar. The main difference, of course, being the frequency span that each of the tools cover. And today we'll have a quick walkthrough, introduction to the virtual demo, just to show you what are a couple of buttons you need to push to access it. And then we'll show off 2 common tests that RF engineers encounter. One of them will be in-band interference, and the other is the tracing of time division duplex signal. Both have some different functionalities. Both of those tests show off different functionality that Spectrum Compact has. So, without further ado, to get to the virtual demo of Spectrum Compact, just follow the link spectrumcompact.com/emulator. You'll find the link in the description below. When you arrive to that web page, you'll be greeted by a quick form that we really want you to fill in to get your contact details, where you only need to submit your name, email, and country to help us understand where the interest for our tool comes from. So, it is very quick. I'll put my details and my working email. Country, if some of you doesn't know yet, SAF Tehnika is headquartered located in Riga, Latvia, right by the coast of the Baltic Sea. So we're signing up and we're ready to use emulator. So what you see in front of yourself is a replica of the Spectrum Compact emulator. It might look different vertical if you are accessing the web page through your mobile phone or any other screen of a more vertical alignment. When you come here, you're free to do whatever you like with the tool. So if you already have in mind some things that you want to test out, maybe you already use one of our tools, so you just want to show to a colleague of yours how to perform a test, that's also a go-to tool, which we use ourselves to discuss parts of the interface of the analyzer. And it's a 2 to 8 GHz tool, and you can see we've modeled some of the signals for purpose of imitating real-world environment and to give us some playground for the analyzer. So yeah, feel free to test out the functionalities and what different buttons mean on your own if you wish to do so. But we've created a couple of tests, a little over 10 tests to show off functionalities and to replicate some of the common tests that the engineers need. To access those, you can go 2 routes. One is the application root, the other one is industry. So just click on the drop down and you'll see a couple of options. So if you kind of have the understanding what are the applications that you might need, there are 4 different categories that we've introduced: 5G test, interference hunting, point-to-point link troubleshooting, or site verification. But if you're not that sure about the applications, but you have the industry, well, just check out the industry selection. We very hope that one of those you feel that represents who you are. If not, write a suggestion in comments what we have not covered, and for a time being, just pick whatever you feel closer to, or maybe go through the different ones, and perhaps there are some tests that you'll just find by you'll be lucky and you just find the right one for yourself. So there are a couple of industries. We've mentioned 5G, well, as an industry too, it has its own specific needs. Then there are distributed antenna system integrators, local government, utilities and transport, mobile operators, carriers, regulatory body, well, agencies, satellite communication industry, system integrator industry, and wireless internet service providers. So for our first test, I want to show you the in-band interference. I think that's a very classic test. So in the applications, select interference hunting, and you'll see there are 4 different interference scenarios that are available: co-channel, in-band interference, out-of-band interference, and wideband interference. I picked in-band interference because I think this shows off the beauty of using spectrum analyzer the most, something that is not that easily done if you work with multimeters on a daily basis. So that's where seeing the whole spectrum really comes into play. So when you see the test that you need, just click on it, and we've prepared some instructions, a real specific set of instructions, so you don't get lost. So you'll find the signal that has that scenario modeled on it. For in-band interference, we've prepared a signal at 4.6 gigahertz, and the instruction usually is laid down in 6 steps, each with its more detailed specific instructions. We've wrote down each button that you need to push, so it might be too much details for someone who has been using Spectrum Compact before, but we just wanted to make sure that nobody gets lost. Although as you walk with me, you'll see that once you've started playing with it, the Spectrum Compact is, well, it's a really intuitive tool. That's something that our team of engineers tried its hardest to achieve. The minimum amount of buttons possible, because obviously when you're in field, perhaps hanging on a tower, not really a place where you want to, well, to discover intricacies of different buttons. We want to make it clear so you get as fast as possible. So the first thing, we need to find the signal. In this scenario, well, our main signal is located at 4.6 gigahertz. We know that something's not completely right with it, so we want to check what's there. So to select center frequency, as described in the instructions, first we click on the FREC button, which opens up a dial pad. Make sure that the center one is selected, and just a reminder, this is a replica of the interface, which is used by, well, it's touchscreen in the original tool, but if you have a touchscreen availability on the device you're using, then you'll have like the best one. I'm using mouse right now, but really doesn't matter that much. We've selected that we want to define the center frequency. We press 4600 to get us to 4.6 gigahertz. and press OK to confirm the selection. Well, we see that there is some signal in there, but we need to make a span a more narrow one. So we've been at the frequency, we push back, we're back to the main menu. We push and that represents the second part of the test, selecting frequency span. We need to select span button and define the span. So as you can see here, for this signal, we're working with something along the magnitude of 100 megahertz. So we input 100 and press OK. It creates setting a span symmetrically around the center frequency, and you can see there is a signal in the middle of the screen. Although we can see there is a beautiful rectangle coming almost across the half of the screen with some spike in the middle of it. And well, that's what we can see is might be causing a problem with us setting up a good communication. This one, I say, looks rather beautiful in terms of easy to detect. Real life scenarios might be different. Sometimes you need to wait some time to just understand whether there is anything. We'll cover that a little bit later. What to do if the signal is changing. But then this thing, we can see a rather static interference closer to the right side of our signal. We're still always aiming for better resolution on the picture. So what we can do next is amplify low noises to see this picture even more clear. So we go back to main menu, we select next step from instructions, low noise amplification. This is something that's built into the tool. It says exactly what it's called. It amplifies noises and makes our tool makes the picture more visible. So we go to level, press L and A button, stands for low noise amplification, and we can see that the signal is more pronounced now. Now that the signal is much more pronounced, the next thing we want to learn about it is the power output that we receive. The Spectrum Compact, is it anywhere close to the our benchmark power? To do that, Spectrum Compact has a built-in power and band frequency functionality, which is basically an integral of the amplitude over the frequency domain. And to do that, we go in power and band submenu, which produces with the next choice is we need to select across how wide of a frequency domain will we measure the power. We might know, and in this case, in the instruction we already wrote for you, that it's 48 megahertz wide, but of course you can tell it by your eyesight. We've selected previously a span of 100 megahertz. We know that Spectrum Compact screen is always 10 rectangle wide, which means that each rectangle is 10 megahertz wide. And we can see it's 40-ish something, but well, we can test it by applying the band measurement. So let me select not 48, but well, I presume maybe it's 55. We select 55 bandwidth, press OK. We see nothing changes. The PAB marker, PAB letter shows that the marker is somewhere away. We don't need to search for it. We have set center button. We push that, and we can see a blue part of the screen which denotes where the power output is measured. So we see it's wider than the signal, that our intended signal. We can scale down. In this scenario, you know it's 48, so no need to do any guesswork. Let's press 48. And yeah, it's much more precise. Well, what is the power output? Is 48 dBm. Here we can see the measurement It wasn't there before. Right next to PIP, blue digits about the channel width. So it's 48, 49 dBms. That's an easy way to learn how strong is the power output we're receiving. What's next? We see the power output. Perhaps it should be different from the one that we expect, although I guess by not a big margin. But more importantly, what we see is that there is an interference in our beautiful rectangle of our signal. There is a spike. To correctly report on it, what we do, we need to determine the center frequency of the interference signal. Well, we can do it by looking at the screen and doing some guesswork. Well, not guesswork, but trying to count rectangles with our eyesight. We have a better option to do that. So let's go push back and go to the next step, measuring interference signal frequency. So now that we're back into the main screen, let's go into the marker submenu. And there is a peak button. What it does, it sets the marker to the highest amplitude that's currently seen on the screen. Let's press that, and we can see peak button. The marker's frequency is denoted in the green digits or right over there. So we know that the frequency of interference signal is 46.9, 46.10, so 9-10 megahertz above the center frequency of our screen. And well, in this case, we can see a confirmation of that because of the width of one rectangle, but not in all cases. It's located as beautifully right on the border, right on the edge of rectangles. So this feature might save you a lot. Okay, so now that we know where a signal is and how our signal looks like, where is the interference coming from, we can then, well, try finding the source of it, or maybe contact the regulatory authorities for them to investigate, depending on how the laws in your country work. What else? There is a rather neat feature in Spectrum Compact that we call tracing. There are a couple of different tracing types. Let's go to that step. It really helps you to put the signal into the perspective. Spectrum Compact is a sweeper spectrum analyzer, so each image on the screen you see in this setup you can see, but it's actually sweeping across the frequency span, and it does so with 1000 kilohertz right now. So it's either fast for it to get across the screen without us really noticing it that much, but to get maybe a more representative statistics, the tracing is a really good set of features that allow us to record multiple sweeps. So we go into trace submenu. Currently it's in the normal mode, so each sweep is, well, it's not recorded, it's shown from new. But if we select cumulative tracing, then you can see that each sweep generates 1 point, and we can gather statistics of noises that are happening there. You can see the green counter changing it, so right now we're just over 120 sweeps, and we can see this one is a rather stable signal, artificially generated, which helps the case, and you can see, well, what is there on a more statistical approach. Once that is done, you can save it for later use. and to be able to, well, show the same statistics later when you're, I don't know, in your headquarters, or to be able just to relate your situation to someone. The same regulatory authority, it's just easier to show them a file than talk about what's happening there. That's all about the first test, the in-band interference. I'll go back to trace, select the normal screen, and go to the main menu. The second test that I wanted to show you is tracing of time division duplex signal. I'm sure most of you know what that is, but just in case, there are two types of communication protocols when the between receiver and sender, because the same tool, the same tower might be used to do both. Well, it usually is used to do both. So frequency division duplex, the frequency at which the signal is received and at which the signal is sent away is split in the frequency. So there is one frequency for receiving and one for sending. But it's more and more popular in the last years. It's growing its use as the time division duplex. You don't need to buy separate frequency channels. In this case, your signal is split not in frequency but in time. So there is a reserved time for sending data, and then there is a reserved time for receiving it. To trace such signals is, well, it's a challenge of their own to understand what's happening, how the same channel, well, what is the channel usage statistics? Is there anything else, interfering with the signal, or just anything plainly does not working correctly with your equipment? So you need to know how does that work. We actually have a really great application note on our website. Check description, there should be a link to that, where we talk about TDD, and in case you might want to learn more details about it, or just enjoy reading more than listening to me, go there. But meanwhile, let's go and check out another test that we have in our virtual demo. Let's select 5G test application, because that's something TDD is really used in 5G tests. And let's select tracing TDD signal test instructions. So first, we need to go to the signal that we're working on. In this scenario, it's at 2.4 gigahertz, so a classic Wi-Fi frequency channel. Let's select FREC to select center frequency, and let's put in there 2411 2411 megahertz, and click OK. So we now see a signal that evolves in time. We can see with our eyes that it is located within some span. Perhaps we want to make that span more narrow. For that, there is the second part of our instructions. Let's go back to the main menu. By now you already know how to do that. Now we go to the span submenu, and we dial in 50 megahertz. Now, so now we're looking closer at the same signal. We might want to turn on low noise amplification if it isn't turned on from the previous test, but I already have it on. I can see it here right on the screen. A little light blue letters LNA on, meaning that low noise amplification is already on. Let's just check the third step, but nothing new there. It's the same thing that we've done in the interference signal. What we might want to do with this signal, though, even though we see it good, we might want to trace out to understand how wide it really is. What are the amplitudes it's coming to? To do that, let's go to detector settings. First, we want to set up how will the Spectrum Compact register each of the sweeps. So we need to go to the trace, and we can see at the top of the interface there are three options: detector average, the one selected right now, detector max, or detector min. What does it mean? Each time the Spectrum Compact sweeps across the frequencies, only one point is drawn, despite there being a distribution of the power received. And that's what detector is about. Right now, each time there is an average recording displayed. What we want to select this time is the maximum one. To understand where it reaches, you can see it's going up slightly. We can select minimum just to see what the difference is. And you can see the signal is shown lower. So let's select detector max once again. We're currently registering maximum of the signals that we receive. And the next thing is what we want to do is start tracing. Let's go to the next part of instructions. We don't need to go to the main menu. We're still using the same submenu, trace submenu. Next is we select the type of tracing that we want to see. Before, we used the cumulative one. Now let's see what the min-max hold is about. And what it will help us do, not produce the points, but at each frequency, it will register only the maximum one achieved throughout multiple sweeps. Let's see for ourselves. As I press min-max, you can see that at first it wasn't that pronounced as a rectangular signal. It was more like zigzaggy, but then with multiple sweeps coming over, and you can see the sweep counter right here in dark blue, it's approaching 200, over 200 sweeps now. Well, across multiple sweeps, it produced a beautiful rectangle with a slight deviation on the very end of it. And we can do that again. Just pressing min-max, it resets the counters, and well, after some time, we achieve the same signal. It's minus 50 dBm all across the table. That's the maximum signal. You can see the minimum. That's very, very stable. So it represents the base noise level, and that's how we create from a really it's not stochastic in this case because it's artificially made, but from a rather changing time evolving signal that is harder to grasp with the eye. We kind of can see where it's located, but to know like a more specific parameters of it, the width, now it's easily achievable. We know that each rectangle now is 5 megahertz, so it's 21, 22 megahertz wide signal. We know its amplitude, its maximum amplitude. So we understand it. Well, we understand its nature, even though not as visible to the eye. Another way to do that is to build a time plot. Let's go to the next part of instructions. Let's go to the main menu. And let's get to the tools and settings. That's where a couple of different things is located. What is interesting for us right now is time plot. For that, we need to click on record time plot. And you see the screen has changed completely. There is no more signal anymore. So to do that, we still can see that our settings are still the same. We're centered at 2411 and it's 25 megahertz to each direction, to the left and to the right of it. LNA is on, so all the settings are still there. And what we want to do is just press new record. What you'll see is it produces row, which represents one sweep of across the frequency. So we can see a lot of sweeps stacked on one another. It gives us a different perspective than the tracing that we've seen before. Let me just press on new record. I'll do that again. And when it's halfway there, when I press new record again, it will save it. And you can see that there are two newly created files, R0005 and R00006, which are images of our that are recordings that were just done. Select the one that you're interested in. This is the last one I did, and then select Open Timeplot. And there you can see it in static. So it's saved on the Spectrum Compact now. You can send it back to your team or check it yourself afterwards in more details on the PC software that we have. Just as I said, each row, each horizontal line represents one sweep. We see a lot of blue noise to the left and to the right of main signal. This is the base level, the base noise level, ground noise level, and in the middle we can feel what we have seen previously with our eyes, but now it's more laid out in front of us. How does each sweep perform? So this one is very chaotic one, but we can still see that there are multiple channels inside of the signal that were used differently. There are ones that are used less, like in the very middle, the one being the more bluish one, and then there are the more red ones that achieve the higher amplitude on a more often level. So that allows you to see your data transmission, to see your signal in a completely different way. So that's about it about TDD signal. What I really want to say is that we have a lot of different tests. Most of them will start you in a very similar way. You need to select center frequency, select frequency span. But then after those two, it's usually some other functionality of Spectrum Compact being shown off. There are plenty more, so check out other tests. There is mask mode, which is great for catching errors, errors or breakdowns from your receiving equipment. Spectrum Compact can suppress harmonicas, so that's something. Check out the multipath test. Those are really shows off what this really small in size, just the mobile phone size device has a great array of functionalities. So that's all, folks. If you have any suggestion about the emulator, about maybe next videos, leave a comment below, or you can contact us through our website contacts part. There is a forum too, whatever is easier to you. And thank you for your attention, and goodbye.